Hello everyone. In this tutorial, we are going to discuss the Moivre's theorem, and we need to recall that in the previous tutorial we have discussed multiplication of two or more complex number in polar form, which of course if I will represent that, if we have our z1, or before I say z1, okay, let's say if we have our z1 is equal to r1 cos theta 1 plus I sine theta 1. Let's say we have our z2 to give us r cos, that is r2 cos theta 2 plus I sine theta 2. Let's say we have our z3. This will give us r3 cos theta 3 plus I sine theta 3, and so on. Now, when we say z1 times z2, z1 times z2 simply gives us r1 r2 cos theta 1 plus theta 2 plus I sine theta 1 plus what? Plus theta 2. Now from here, it means that if we have z1 times z3, z1 times z2 times z3, we're going to have r1 r2 r3 cos theta 1 plus theta 2 plus theta 3 plus I sine theta 1 sine theta 2 sine theta 1 plus theta 2 plus theta 3. So what it means is that, what if z1 is equal to z2 and is equal to z3 and is equal to any value, let's say is equal down to zn, assuming any value of n. It means that we can represent this general form as z1 can be represented as r cos theta plus I sine theta. We can represent z2. Since z2 is the same thing as z1, we are still having r cos theta plus I sine theta. We still have z3, which is still the same thing as this. It means that from here, z1 times z2 is going to give us r square, which is r1 times r2, into cos 2 theta plus I sine 2 theta. It means that if we have z1 times z2 times z3, this is going to give us r raised to power 3 into cos 3 theta plus I sine 3 theta, because here you're going to have r times r, which will give us r raised to power 3, cos open bracket theta plus theta, which will give us 3 theta, plus I sine theta plus theta, which will also give us what? 3 theta. It means that we can now attribute a general form for the, because when you say z1 times z2 and they are the same, we can represent this as z raised to power of 2. When we say z1 times z2 times z3 and they are the same, we can express this as z raised to power 3. So we can express a general form for z raised to power n, which will give us r raised to power of n into cos n theta plus I sine n theta, and z raised to power n is equal to r raised to power n into cos n theta plus I sine n theta now represents something. Now, don't forget, this z is the polar form, is representing the polar form of the complex number from what we have been doing here. And the polar form of a complex number is z is equal to cos theta plus I sine theta. So now, since we have gotten z raised power of n to be equal to r raised power n into cos n theta plus I sine n theta, instead of writing the z, I'll now substitute cos theta plus I sine theta. It means that this is going to give us, open bracket, cos theta plus I sine theta, everything raised to power of n, is equal to r raised to power n into cos n theta plus I sine n theta. Now, this is what is referred to as our De Moivre's theorem. Now, you can use De Moivre's theorem to expand when you have a complex number in the polar form raising to a power. For example, z raised to power 2, z raised to power 3, z raised to power 4, z raised to power 5, and so on. You can use De Moivre's theorem to solve that. Now, you can also now use this application of De Moivre's theorem in application of trigonometry to also get some trigonometrical identities. And that is where we are going to start from. So, but before we discuss the trigonometrical identity part, let's use it to illustrate an example under powers first. Now, we are to evaluate this complex number that is in polar form raised to a power of 4. Now, again, from what we just derived, we have derived that z raised to power n is going to give us our r raised to power n, open bracket, cos n theta plus I sine n theta. So here, our z is equal to 2 into cos 37 plus I sine 37. So since our z is equal to this, it means that our r here, our r is equal to 2, our theta is equal to 37, then n is equal to the power which we are raising it to, which is what? 4. Now here, it means that z raised to power of 4 is going to give us r raised to power of 4, that will be 2 raised to power of 4 into cos n theta, that will give us 4 times 37 plus I sine 4 times 37. So z raised to power of 4 is going to give us 2 raised to power of 4 is 16 into cos. Now 4 times 37, 4 times 30 is 120. 4 times 7, that's 28. So that will give us 148. So 4 times 37 will give us 148 plus I sine 148. So it means that z raised to power 4 will give us 16 into cos 148 plus I sine 148. That will be the value of 2 cos 37 plus I sine 37 raised to power 4 will give us 16 into cos 148 plus I sine 148. So that will be the answer to that question. So that is how to evaluate a complex number in polar form as repetitive consecutive powers, raised to power 2, raised to power 3, raised to power 4, raised to power 5, and so on. So now, how can we apply De Moivre's theorem as How can we apply the Moivre's theorem in trigonometric identities? Now, trigonometric identities of multiple angles using complex number. We have to remember that there is a fundamental trigonometric identity which we have when we are studying trigonometry, and that fundamental trigonometric identity is sine square theta plus cos square theta will give us 1. The Moivre's theorem states that z raised power n is equal to r raised power n into cos n theta plus I sine n theta. So here the polar form for our complex number z is equal to cos theta plus I sine theta. So it means that instead of writing z raised by n, I will now write cos theta plus I sine theta raised by n is equal to r raised by n into cos n theta plus I sine n theta. So now that we have already gotten this, if we call this our left hand side, now if we call cos theta plus I sine theta raised by n our left hand side, and we call I raised by n into cos n theta plus I sine n theta our right hand side, what it basically means is that if we are to consider the left hand side first, it means that our left hand side is equal to cos theta plus I sine theta raised to power of n. Now, if our left hand side is open brackets cos theta plus I sine theta raised to power n, don't forget cos theta here can be related to as A. I sine theta here can be sine theta here is related to what? Can be related to what? B. So it means that our left hand side is going to give us A plus IB raised to power what? Raised to power of n. Now, for example, if our n is equal to 3, now take a look at this. This is where you need to pay attention. If our n is equal to 3, let's say that let n to be equal to 3. If n is equal to 3, it means that our left hand side is going to give us A plus IB raised to power of 3. A plus what? IB raised to power 3. But don't forget that left hand side is cos theta plus I sine theta raised to power 3. So if I rewrite this, cos theta plus I sine theta raised to power 3 to give us A plus IB raised to power of 3. So here it means that cos theta plus I sine theta raised to power 3 will give us now A plus IB raised to power 3. From Pascal triangle, we know that x plus y raised to power 3 is going to give us x raised to power 3 plus 3x square y plus 3x y square plus y raised to power 3. So using the same concept here, it means that A plus IB raised to power 3 is going to give us our x will be A, our y will be IB. So this will give us A raised to power of 3 plus 3A square I b plus, now going to the next, we have done x raised to power 3, we have done 3x squared y. Now going to the next, which is plus 3xy squared. This will be plus 3. Our x is what? Our x is a plus 3a. Y squared, our y is ib. So this will be ib raised to power of 2 plus y raised to power 3, which is the last one. So that will be ib raised to power of 3. So from here, cos theta plus I sine theta raised to power 3 is going to give us a raised to power 3 plus 3a square. Now using this b, 3a square times I times b will give us 3a square bi plus, now okay, let me write this out. 3a times I square times b square plus I raised to power 3, I raised to power 3 times b raised to power 3. So this will give us cos theta plus I sine theta raised to power 3 is going to give us a raised to power 3 plus 3a square bi. Now I square is minus 1, so this will be minus 3ab square. Now I raised to power 3 is the same thing as I square times I square times I will give us I raised to power 3. So it means I raised to power 3 is equal to minus I. So this will be minus b raised to power 3i. So here, cos theta plus I sine theta raised to power of 3 is going to give us, we collect the like terms, those that are the real parts. We connect real part and real parts, then imaginary parts and imaginary parts. So the real parts first, we have a raised to power of 3 minus 3ab square plus, now if we factorize I out, we'll be left with 3a square b minus b raised to power 3. So a raised to power 3 minus 3ab square plus I into 3a square b minus b raised to power 3. So now, cos theta plus I sine theta raised to power 3, that is multiple powers, what we did earlier. It means that cos theta plus I sine theta raised to power 3 is going to give us, it means that cos theta plus I sine theta raised to power 3 here is more like your R value here is 1. So this will just give us cos theta 1 plus cos theta 2 plus cos theta 3. But the theta 1, theta 2, theta 3, they are the same. So it means that this is going to give us cos 3 theta plus I sine 3 theta is equal to a raised to power 3 minus 3ab square plus I into 3a square b minus b raised to power 3. So here, you will now see that the left hand side here is corresponding to the right hand side. And why will I say it's corresponding? We have a real part here. We also have a real part here. We have an imaginary part here. We also have an imaginary part here. It means we can get two derivations from this particular equation. Now, what are those two derivations? Now, the first derivation that we can get from here, the real part here, which is cos 3 theta is equal to the real part at the other side, which is a raised to power 3 minus 3ab square. And we can have another derivation as the imaginary part here is equal to the imaginary part here. It means that I sine 3 theta is equal to I into 3e squared b minus b raised to power 3. So here, of course, this I will cancel out. We should have just even because it's the imaginary parts that we are comparing to each other. So here, this is sine 3 theta is equal to 3e squared b minus b raised to power 3. So from here, since cos 3 theta is equal to a raised to power 3 minus 3ab squared, and don't forget, we took our a to be equal to what? Cos a is equal to cos theta, while our b is equal to what? Sine theta. So from here, cos 3 theta is going to give us a raised to power 3 cos theta raised to a power of 3 minus 3 cos theta, our b, sine theta raised to a power of what? Raised to power of 2. So it means that cos 3 theta is going to give us, now cos theta raised to power 3 is cos cube theta minus 3 cos theta sine square theta. But sine square theta plus cos square theta is equivalent to 1. It means that sine square theta is equal to 1 minus cos square theta. So here it means that cos 3 theta is equal to cos 3 theta minus 3 cos theta into sin square theta, which is 1 minus cos square theta. So here cos 3 theta is going to give us cos cube theta minus 3 cos theta plus 3 cos cube theta. So minus times minus will give us plus. Cos theta times cos square theta will give us cos cube theta. So cos 3 theta is going to give us cos cube theta plus 3 cos cube theta will give us 4 cos cube theta minus 3 cos theta, and cos cube 3 theta is equal to 4 cos cube theta minus 3 cos theta is a trigonometrical identity. So you have discovered that using the Moivre's theorem, we have been able to prove why cos 3 theta is equivalent to 4 cos cube theta minus 3 cos theta. So the same approach here, if we say that sine 3 theta is equal to 3 multiplied by a square, that's cos square theta, our b, sine theta minus sine cube theta. So now you will now use the same approach. Sine square theta plus cos square theta is equal to 1. It means that this cos square theta is going to be 1 minus sine square theta. You substitute that value here. At the end, you are supposed to get our sine 3 theta to be equal to 3 sine theta minus 4 sine cube theta. So if you don't get this, it means that you have did a mistake here. What I said you should do again is that you take cos square theta. Cos square theta will be 1 minus sine square theta. So anywhere you see cos square theta here, you substitute 1 minus sine square theta. So you use that sine theta to multiply this. You collect the like terms. You are supposed to get sine 3 theta to be equal to 3 sine theta minus 4 sine cube theta. So, and this is where we are going to stop for this particular tutorial. See you in the next tutorial.